Okay, so we're just gonna do a video lecture today. I'm gonna work through those notes that I posted, do some examples. So we'll go through section 8.5, section 8.6, and section 8.7, and that should cover basically everything from that will appear on your guys' exam. 8.5 is going to be on power series. So power series are just a special type of series, right? So these power series, it's a series of this form right here. So it's the sum from n equals 0 to infinity of a sub n times x to the n. So if we write out a couple of these terms, it's just a 0 plus a sub 1x plus a sub 2x plus dot 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 all the way up to plus a sub n. Oops, sorry, this is x squared, a sub n x to the n plus dot dot dot. So it goes on to infinity. So it's an infinite series, right? So this is the form that it is, or we can also write it as a sub 0 times x minus b to the 0, but that's just 1, plus a sub 1 x minus b to the n plus a sub 2, or sorry, not to the n, just to the 1 plus a sub 2 x minus b squared plus dot 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 all the way out to infinity, right? And so the thing that's different about these series here is that we have these x's in here. So now our series are actually functions of x, right? So they have an x inside, and this becomes important later on. But the difference between these are both power series, but we just say this is the power series centered at x equals 0, and this is the power series centered at x equals b, right? So that's where the shift comes in. You could think of this guy right here as x minus 0 to the n, right? So in that sense, it's centered at 0, right? So you'll just keep that in mind when you hear it. They might ask you for the power series of a function centered at a certain number. And so you just have to keep that in mind there, right? And so what we want to do now is that because we have these values of x, our convergence might change depending on what x value is. And so it becomes important to ask, well, what x values does this series converge, right? So, clearly for, let's call this 2, and this 1, right? This is 1, this is 2. For 2, the series converges when x equals b, right? Because when x equals b, this series just ends up being the series of zeros, right? It's not very interesting, right? So cool that it converges at x equals b, but that's not really helpful. So we want to figure out a range of x values that this can possibly converge for, right? It will always converge for x equals b, or in the case of the series centered at 0, x equals 0, because we'll just get the zero series. But we want to be able to look at a larger range of x values for which this converges. So let's do an example and we'll see what I'm talking about, right? So for what values of x does this series converge? Well, almost always with these problems, you're going to be doing the ratio test. So let's consider the ratio of an plus 1 over an, right? We want to take the absolute value of here. We need to keep the absolute value in play here now, right? Even though before when I said if there's no alternating term, we don't have to use the absolute value. But in this case, we do, right? Because x can be anything. So it could be possible for x minus 3 to the n. It could be possible for this guy up here. to be negative, right? For some values of x, specifically for x less than 3, right? That's always going to be a negative number. So it's important to still keep the absolute value here. So we're just going to work through this, right? We're going to do, well, a n plus 1, we're just going to add wherever we see an n, we're going to do n plus 1. So I'm going to write x minus 3 to the n plus 1 over n plus 1. And I'm going to divide, and instead of dividing, I'm just going to multiply by the reciprocal, the a sub n. So this is just n over x minus 3 to the n, right? So what do I want to do? Well, we want to simplify this down as much as I can, right? So x minus 3 to the n plus 1, well, that's just x minus 3 times x minus 3 to the n, right? By properties of exponents, and then times n over n plus 1 times x minus 3 to the n. Oh, and I dropped my absolute values, but we're going to need those still, right? So let's move this around and do some absolute values here. Cool. So we have our absolute values. We see some things cancel out, right? We get an x minus 3 cancels out, x minus 3 to the n cancels out there. And what we end up getting is we just get, this is equal to x minus 3 stays in the absolute value, right? But the n over n plus 1, n's always going to be a positive number, right? Or at least non-negative. It's going to be 0 to infinity, something in there. So we can write this just as n over n plus 1, right? Well, we want to figure out, let's see, what the limit of this is. So there's a couple different ways we could figure out what the limit as n approaches infinity of the absolute value of a n plus 1 over a n, right? I could rewrite this guy up here. Let's rewrite this as x minus 3 times, if I multiply the top and the bottom by 1 over n, right, I get 1 over 1 plus 1 over n. Right, now I don't have to worry about, you could do a L'Hopital's rule on this, right? In like a discrete sense, you could change these to x's and then do a L'Hopital's rule to calculate the limit, right? Because if I send this to infinity, then I'm going to get infinity over infinity. That's an indeterminate form. We're not allowed to do that. But I just rewrote it as this by multiplying by 1 over n times 1 over n, right? That's just 1, so it's okay. And we simplify down to here. The limit of this is just going to be equal to absolute value of x minus 3, right? Because the limit as n goes to infinity, this is 1 over 1 plus 0. So it's just 1 over 1. So we get the limit is this, right? And we want, for convergence, right? For convergence, we want the limit as n goes to infinity of a n plus 1 over a n to be less than 1, right? That's our condition for convergence. So that means that we need x minus 3 less than 1, right? That will ensure that our sum converges for all the x values that satisfy that. So, well, you can just figure out, you can do this a couple different ways, right? What this absolute value means is that implies that negative 1 is less than x minus 3 less than 1, right? That's what the absolute value means. We can rewrite that like that. And then we can just solve for x, right? So that means that x, add 3 to both sides, right? So I do plus 3 here, plus 3, plus 3. I get that canceling out. I just get x is less than 4 and greater than 2, right? So for any x in, that's what this symbol means. This like little E symbol means in 2 to 4, the interval 2 to 4, our series will converge. Will converge. Right? So I know that will converge, and what we call this convergence, right, the length of this interval, this length, I don't know why in my notes, I think when you guys look at this, I have it as 1 as the radius of convergence, but obviously the distance between 2 and 4, or actually, no, you're right, never mind. So the distance between 2 and 4, this distance, is the interval of convergence. Which is equal to 2 times the radius of convergence. So the radius is just half this distance. If you think of this interval as a distance, so that implies the radius, and we'll get into this later, radius of convergence is equal to 1, right? So you can see that on the, I'll write it over here, on the number line, right? If I have 2, and then 3, and then 4, right? This distance here, this distance is 2, but my radius of convergence specifically is 1, right? The radius, if you thought of this as a circle here on this number line, and there's a good reason why we call it radius. It has to do with complex numbers, but we're not going to get into that. But that's why this function here has what we call radius of convergence 1, because that's the radius of this circle. Okay, so we'll look at this next theorem, and we'll do a couple more examples. So if that was somewhat unclear, don't worry, we'll tackle it again, right? So one of our theorems says that given this power series, right, so this is just a general power series. I wrote it a little different than before just to expose you to some other letters, but it's exactly the same. So it's the series from n equals 0 to infinity of Cn times x minus a to the n, right? We have that one of the following must be true, right? So we know that the series converges only when x equals a. That we know for a fact that the series will converge when x equals a, right? So if x equals a, this is going to be 0. It's going to converge to the 0 sequence. So no matter what, that will always be true, right? The other thing that could happen is that the series converges for every x value. So it doesn't matter what x value we pick, will always satisfy our condition for convergence. And we'll see an example later on, and I'll show you why we know that it works for all x, right? And then the third condition is that there is some positive number r such that the series converges if this absolute value of x minus a is less than r, and it diverges if it's greater than r. And that's what we had up here, right? In our previous example, we found that x minus 3, that's our x minus a for this series, right? X minus a to the n. Our x minus 3 was less than 1, right? So that was our radius of convergence. Our radius of convergence was 1. And that's what this r is, the radius of convergence, okay? And so we converge if we're an x value within that interval. So for any x in this interval up here, our series will converge. But if we're outside of this interval, then we no longer satisfy this condition, and so our series would diverge, okay? So this theorem doesn't tell us what happens when x equals r, right? So at the end points of this interval. So it actually doesn't tell me what happens when x equals 2 and x equals 4, right? This is an open interval. It doesn't give me closed brackets. So to figure out what happens when x equals r, we need to test the endpoints of our series. And that can be a little bit of work, but it's really usually not so bad. So we'll do some examples. But if you're asked to find the interval of convergence in a problem, you have to test these, right? So you must test these. If you have questions on your exam, whether you need to test the endpoints, go ask Dr. Blanton, or you can come ask me. I don't think I'll be proctoring your exam, but you can come ask me and I can try to help you. So let's consider another example. So we're going to consider this series, right? So we're going to go through it, find the interval of convergence, and then we're going to test the endpoints, right? So the interval of convergence is the same problem, right? I'm going to consider an plus 1 over an. I'm going to do absolute value, right? And so this is equal, wherever I see an n, I'm just going to add an n plus 1. So I get absolute value of negative 3 to the n plus 1, x to the n plus 1, over the square root of n plus 2. Okay, so square root of n plus 2, because it's n plus 1 plus 1, so that's plus 2, right? And then I'm going to multiply by the reciprocal instead of dividing, so I just get square root of n plus 1 over negative 3 to the n, x to the n. Okay. And then absolute value, right? So I'll just expand these all out. If what you'll notice is actually, I can write this out one more time. I'll expand this real quick. The negative 3 to the n plus 1, when I take the absolute value, I can just rewrite this as 3 to the n plus 1, right? I don't want to deal with that negative number. The absolute value is going to change it positive no matter what, so I'm just going to keep it as positive. Square root of n plus 1 over, again, I'll put the square root of n plus 2 over here just to keep it near its buddies, and then we do 3 to the n, x to the n, right? So what I see is going to cancel here is I'm definitely going to cancel this with the 3n. I'm still going to have 1 3 left over, and the x to the n with this x to the n, I'm still going to have 1x left over, right? So in the end, I get that this is equal to, I said there's a 3 left over, there's an x left over, right, times the square root of n plus 1 over the square root of n plus 2, right? And absolute value, I can simplify this a little bit more. I can do this as 3 absolute value of x. The absolute value of these square roots, those are going to be positive, so I don't have to worry. 3 is always positive. So I can stop dealing with absolute values for those, and I can rewrite this as square root of 1 plus 1 over n, right? I just factored out the n and then divide by square root of 1 plus 2 over n, right? And that square root. Okay, so we get that the limit as n goes to infinity, ooh, that's not a very good infinity, of an plus 1 over an is equal to, let's do 3 absolute value of x times the limit as n goes to infinity of square root of 1 plus 1 over n over 1 plus 2 over n, square root there, right? So as n goes to infinity, we get 1 plus 0, right? So as this goes to infinity, we get 1 over infinity, which becomes 0, and then we get 2 over infinity, that also becomes 0, so we just get square root of 1 over square root of 1, that's just 1, right? And so we get that this limit is just equal to 3 square root of x. Okay, so what's our condition for convergence, right? We require that this is less than 1, right? And so that we get, that implies that x, absolute value of x, is less than 1/3, right? Divide by 3. So this is our radius of convergence, right? X minus a. In this case, a is 0, right? So this is x minus 0, absolute value, is less than 1/3, right? So our radius of convergence, radius of convergence is 1/3, right? And so we can figure out exactly what the interval is by saying, well, x is less than 1/3 and greater than negative 1/3, right? So our interval of convergence is negative 1/3 to 1/3, right? You can test that the radius of this is 1/3, but it's pretty clear that it is, right? Half, this is centered at 0, so half that distance is 1/3, right? So this is our interval of convergence, but now we need to check the endpoints, and this is where I'm gonna come out of room. Check the endpoints. So I'm gonna go ahead and add a page to this real quick. Unfortunately, you guys can't, but just figure out where to squeeze it in on an extra piece of paper, or if you're just watching and taking notes, then you'll be able to add as much room as you need, right? So we want to check the endpoints. So we're gonna do for x equals negative 1/3 first, right? So in this case, our series becomes the series from n equals 0 to infinity, right? What was our series? Our series was negative 3 to the n, x to the n over this, right? So we just plug in our 1/3. So we get negative 3 to the n, negative 1/3 to the n over square root of n plus 1. Well, I can combine these, right? They have the same x. I can combine these guys, right? They have the same exponents, right? So, well, negative 1/3 times negative 3, that's just 1, right? So this is just equal to, or negative 1/3 times negative 3 is actually just 1, right? So this just becomes 1 to the n over, and 1 to the n is just 1. So we get from n equals 0 to infinity of 1 over the square root of n plus 1, right? Oh, never mind. Whoops. Sorry. My radius of convergence here, let's see. Was that a negative 3? Oh, we're testing positive 3. Yes. Nope, that's right. Okay. So we're good here. And so how can we test the convergence of this? It's not alternating. You could maybe do a comparison test. But I think the easiest thing to do would be the integral test. So integral test, little test, right? This is a non-negative, right? This function right here is non-negative, and it's decreasing. So we can use the integral test, right? So we're going to, what was my sum from? Was it from n equals 0? It was from n equals 0. Let's think about this. I'm going to go ahead and change. I mean, it doesn't matter. We can do it directly. So this is from n equals 0 to infinity of 1 over the square root of x plus 1 dx, right? So this is equal to the limit as x approaches infinity of the integral of 1. Oh, I don't want x. That's 2 x's appearing. The limit as, let's do b approaches infinity. 1 to b of 1 over the square root of x plus 1 dx. Okay, so integral is pretty easy to do. It would be really nice if this was just I don't know why I wrote a 1 again. It's just false hope. It'd be nice if this was a 1 to infinity, because then the integral would be easier to do, but it doesn't really matter, because if I say, let's do a u substitution, let u equal x plus 1, then du is going to be equal to dx, right? Okay, so then my limit becomes the limit. B still goes to infinity, right? Nothing changes. The integral, well, this was x equals 0 to x equals b. So this is going to be from u equals 0 plus 1 is 1 to x equals, u equals b plus 1 over the square root of u du, right? Now this is actually really easy. I can actually not even concern myself about this. I can just say that this is equal to the limit from 1 to infinity of 1 over u to the 1/2 du. And this diverges, right? Since p is equal to 1/2, and that's less than 1, right? So by the p-series test, this actually diverges. So you could go through and you could actually calculate this explicitly and do the limit if you want, but if you just did this u substitution, you just get that it diverges by the p-series test. Okay, so we know that what that means is that negative 1/3 is not going to be included in our final interval of convergence, right? So now what we need to do is we need to now test x equals 1/3, right? So you can see why you said this is a little bit tedious, because you're solving 3 problems for the price of 1, which isn't very fun, right? We want to solve less problems, not more, but it's not so bad, right? It's all the stuff that we were doing before. N equals 1 to infinity of negative 3 to the n times 1/3 now to the n over square root of n plus 1. Right. Well, this problem is a lot easier because this one simplifies, right? This simplifies to, just like the other one. I keep writing n equals 1. It should be n equals 0. The negative 3 cancels with the 1/3, but now I get a negative 1 to the n over the square root of n plus 1. Well, as it so happens, this converges by the alternating series test. Right, so as long as it's alternating, it's decreasing, right? The alternating series test says if Bn is decreasing and Bn goes to 0 as n goes to infinity. Well, our Bn, right, is just the 1 over n, or 1 over square root of n plus 1. That's clearly decreasing, just like we said earlier, right? And clearly the limit as this goes to infinity is 0, because as n gets really big, this denominator gets really big, it goes to infinity, and so this ends up going to 0, right? So we're good there. Maybe I'll do it in green. And so that quickly converges. So oftentimes one of them will be a lot easier than the other, but you still have to check both. And so our actual interval of convergence is negative 1/3 was not included because it diverged, but 1/3 was included, right? So maybe you could say I, our interval I. So it will converge when x equals 1/3, and it diverges when x equals negative 1/3. and so we don't include it, right? Our radius of convergence is still the same, right? Adding that endpoint doesn't change the length of that interval, really. It's just an infinitesimal length. And so we're not changing anything, so our radius of convergence is still 1/3, but our interval of convergence is now more defined to be -1/3 to 1/3. Okay, so I think I pulled this next example from your worksheet, so go ahead and check on your worksheet. This might be in your worksheet. I can't remember. I did it a long time ago, so I can't remember, and I don't want to pull up your worksheet right now because I want this lecture to not take a million years, but you're given this thing called a Bessel function of the first kind. So we call it of the first kind if it's a J. If it's of the second kind, it's a Y. And you'll get into these if you're a physics major, math major, or an engineering major. These are special solutions to different differential equations. They're called special functions. And they're really quite interesting. But we won't get into it, but we'll just tackle this problem. But you get to see kind of stuff down the road, okay? They're really useful for solving differential equations, specifically the heat equation in what's called cylindrical coordinates, okay? Anyways, so we're going to consider that. And so we want to find the radius of convergence of this, right? So we want to figure for what x values does this series actually converge. And considering these are special functions for solving differential equations, you might want them to be really well behaved, right? So you hope that they probably converge for every x value. So we'll keep that in mind while we're solving this problem, right? And so we want to consider, just like we have, an plus 1 over an, right? So if we consider this, we're just going to add an n plus 1 wherever we see an n, right? So this is going to be equal to, slap an absolute value, we do -1 to the n plus 1, x to the 2 times n plus 1, right? Over 2 to the 2 times n plus 1 times n plus 1 factorial squared times the reciprocal, right? So now times 2 to the 2n n factorial squared over -1 to the n x to the 2n, right? And again, we can actually drop these negative values because we're going to be in absolute value, so I can just drop those. So I'm just going to erase them now instead of rewriting the whole thing. Okay, so let's expand some stuff out. So -1 to the n plus 1, that's just, or 1 to the n plus 1, that's just going to still be 1 the whole time, right? So actually don't even need that one. So this is actually just x to the 2n plus 2 times 2 to the 2n times n factorial squared. Okay, and then over, I get 2 to the 2n plus 2, but that's just 2 to the 2n plus 2 times n plus 1 factorial squared, what a mess, times the 1 to the n goes away, and I get x to the 2n, right? Okay, so let's see what kind of cancels. So I can rewrite this as, this is going to be x to the 2n plus 2, that's just x to the 2n times x squared, right? We're good there. And then I get 2 to the 2n. I think that's going to just stay the same. Yeah, we're going to do times 2 to the 2n times n factorial squared. So we split up that one, and then let's split up this bottom one. I get 2 to the 2n times 2 squared times, well, this is, remember, let's say this guy, this is actually just n plus 1 times n factorial, right? And then this is squared. And by properties of exponents, that's n plus 1 squared. Oh, that's not a 2 squared times n factorial squared, right? Okay, so I'm going to write that out down here. And so I get n plus 1 squared times n factorial squared. And what do I else get? I still get x to the 2n. Okay, now we see a lot more cancellation. Let's see. So I get the x to the 2n's cancel. I get the n factorials cancel. And I get the 2 to the 2n's cancel, right? So all I'm left with is now I can pull out the n factor, anything with n. I just have to leave the x in the absolute value, right? And do I? I don't. I don't think I even have to, right? We don't have to do that because, well, let's just leave it. We don't have to do it because if I square it, it's always going to be positive. So it doesn't matter what x is going to be. So this ends up just being x squared over 4 times n plus 1 squared, right? And we can maybe FOIL this out a little bit. Well, I don't even care. It doesn't matter because the limit, we just want to calculate the limit of this, right? We want the limit as n goes to infinity. You could FOIL this out if you want, but you don't need to, right? The limit as n goes to infinity of an plus 1 over an is going to be equal to the limit as n goes to infinity of x squared times, well, x squared over 4, right? We only care about the things that are in terms of n when we're considering this limit, right? So n plus 1 squared, right? I can pull the squared on the outside because let me pull my thing back, because this guy is just 1 over n plus 1 squared, right? The squared, it doesn't matter. If this square goes onto this 1, it's still 1. And then I get that guy squared. So it doesn't matter. If that concerns you, just look at it for a little bit and you should be fine. But this is just equal to x squared over 4 times the limit as n goes to infinity of 1 over n plus 1 squared. Well, 1 over n plus 1, we know that goes to 0. 0 squared, 0. So this is equal to x squared over 4 times 0, which is equal to 0, right? And our convergence condition is that we want this less than 1, right? So for what values of x is 0 less than 1? Well, there's no x, right? There's no x in there. It doesn't matter what x value I pick. I'm always going to get 0, and that's always going to be less than 1, right? So we see convergence is independent of x. That means that the radius of convergence is, you could say it's infinite, or the interval of convergence is equal to negative infinity to infinity, right? Or you could say it's r, right? This means the real numbers. That's what this symbol means. Okay, so this is a pretty easy. I probably wouldn't write that the interval or the radius of convergence is infinity. It is, but I would more so just write that the interval of convergence is that, or that this series converges for all real numbers, you could say, right? But so in this case, when we get an actual number, right? If I get a number when I calculate this limit, and that number is less than 1 in absolute value, right? We took the absolute value. So I shouldn't get a negative number here, right? Because I took an absolute value. But if this number here is less than 1, then it will converge for any x value. If this number was greater than 1, right, then this diverges for any x value. Like, it doesn't converge for anything, right? So just be careful about that and keeping an eye out for that. But usually it will go to 0. It's pretty easy. But it could, the value could be like 1/2, right? And then it's still less than 1. And so it converges for all real numbers, okay? So with that being said, we're going to move on to section 8.6. And so we're going to consider this function. We're going to consider this function. The function, this is my shorthand for function, f to the n with a underscore f of x equals 1/1 minus x, okay? So we know that this has a series representation of this form n equals 0 to infinity of x to the n. And this is going for absolute value of x less than 1, right? And I say we know it has a series representation like this. And I say that like you guys should know it, and technically you do know it, but you might not see it. So why? Why? Well, this is a series, a geometric series, sorry. A geometric series with initial value 1 and the radius r equals x, radius x. So, right, this converges to a/1 minus r, right? That's what our formula is, and that's 1/1 minus x. So this converges, and when did we say that geometric series converged, right? When the absolute value of the radius was less than 1, right? So that's how you can see this. We can easily get it from our geometric series formula. But this is a very important series in math. It's called the Neumann series. You won't see it called the Neumann series anywhere until you get to much more advanced math where you're dealing with things called operators. So this is like defining a this function for matrices. Anyways, it's not important, but it's fairly interesting. If you have questions, let me know. But it's just a very important series in math that we have, right? And so we're going to do some examples. So we want to be able to represent many other functions. We won't be able to represent all functions, but many other functions using this series. And so what we're going to do is we're just going to algebraically manipulate them to be in this form, right? So our goal is to manipulate the function into looking something more like 1/1 minus x, and then rewrite it as a power series. So first, let's pull out the x cubed, right? Because we don't have a x in the numerator. We only have that in the denominator of the function that we want, right? Our goal function here, it doesn't have anything in the numerator. It just has a 1. So we want to pull out the x cubed. So let's say pull out x cubed. Right? So I'm going to write this as x cubed times 1 over x plus 2. Right? And so, it doesn't really matter. I can flip this denominator around, like, right? So this is still equal to x cubed over, we have, in ours, it's 1 minus something, right? So this is 1 over 2 plus x, right? So just to get a little bit more in the form. And then our form has 1 minus something here, right? But in what we have here, we have 2 plus something, right? So I'm going to factor out that 2. So I'm going to factor out a 2. factor out a 2. So I get x cubed over 2 times 1 over 1 plus x over 2, right? So I factored out the 2 from the denominator, and I get that, right? Okay, well, we want the denominator to be something, 1 minus something, not 1 plus something. So I can kind of pedantically rewrite as x cubed over 2 times 1 over 1 minus negative x over 2, right? So now this is something, I have stuff, times 1 over 1 minus something. Well, I know, in general, my series representation of something that's written as 1 over 1 minus something, right? That's something like that. I know that this has this form, right? So I'm going to go as, so we have that, what was our original thing? X cubed over x plus 2. So we have x cubed over x plus 2. This is equal to x over 2, put a cube up there, times this sum, or sum from n equals 0 to infinity, of our something to the n, right? And our something in this case is negative x over 2 to the n, right? Right? And so I get this whole mess, but I have this x cubed out here, so I'd like to bring that guy in. So I can bring that in here. I get a 2 over here. So I'm going to rewrite this actually as x cubed over 2 times this sum from n equals 0 to infinity of negative 1 to the n, x to the n, over 2 to the n, right? I just want to get the n's on each thing. Get that alternating term by itself, get the x's by itself, get the 2 by itself, right? And now when I pull this x cubed in, I get that this now is the series from n equals 0 to infinity. My negative 1 to the n doesn't change. My x, I get 3 more, right? So I get n plus 3 over 2 to the n plus 1. I get 1 more 2 in the denominator, right? And so then I've fully written my whole function as a series. You can go through and check by doing the ratio test on this series to see that, in fact, that this does converge. This series converges to something, and that series will, in fact, converge to the value of this function at that x value, but only for x in, but only for x, the absolute value of x less than 1, which implies that x in negative 1 to 1, right? And you can think about whether it includes those endpoints. One endpoint that you could see that it probably doesn't include is 1. Why? Well, when it's 1, what does this converge to? Or actually, yeah, what does... actually, it might be fine. Never mind. Up here, 1 is fine because you're not going to get 0. So both endpoints might be fine, but you should be careful and just check them if you want. But that's not the point of the problem. I just want you to be able to write this as a power series. You can go through and do the ratio test on this and see if it converges and for what values it converges for. But that's not the point of the problem, right? So the usefulness of representing a function as a power series is, it seems weird because this function up here is pretty easy, right? That's a pretty simple function. Integrating it's not that hard actually, right? You need to do partial fraction decomposition, or maybe a nice U substitution would work, but I mean, not hard, right? That's something we would have asked you in the beginning of the semester. But where this becomes useful is in more complicated functions, but because this looks messier. But anyways, what it becomes useful for is we're going to take advantage of the linearity of the integral and the derivative. And what I mean by that is that you can bring that integral inside of your sums, right? So that's what this theorem says. It says if we have a power series representation for a function with a non-zero radius of convergence, that means that it doesn't only converge when x equals 0, right? Or for one value of x. This radius has to be greater than 0, right? The radius obviously isn't less than 0. Radiuses are a measure of length. We don't talk about negative length, right? So the radius is greater than 0. Then this series representation of the function is differentiable and it's integrable on the interval where it converges, right? So this is centered at A, right? So centered at A, and its radius of convergence is R, right? So I get plus and minus R. So if this was 0, this would be negative R to R. And that's exactly what we did. Let's see. Here, right? Negative R to R. We were centered at, let's see, where is our function? Centered at x at A equals 0, right? So it looks a little fancy, but it's not. It's just telling you that it's integrable and differentiable on this interval, all right? So, so if we go back to actually the special function problem, sorry, I keep scrolling, our interval of convergence was negative infinity to infinity. So that means that this function is integrable, meaning that its integral exists and you can differentiate it everywhere, right? So it's a pretty nice function. It's a smooth function. Let's see, I went too far. Here we are, right? And so all this is saying where the integral and derivative are calculated term by term. So if I have my function and I want to take my derivative, that's the same thing as taking the derivative of the sum, right? And I can bring this sum inside the integral, or inside the, I can bring this derivative inside the sum, right? So that's all it is. And now I'm just taking the derivative of this polynomial. That's really easy. We just do the power series test, right? Same thing for the integral. This integral, well, this function can be rewritten as the sum. You can bring this integral inside. This c sub n is a constant. So you bring the integral here. This is just a polynomial again. So we use the power rule, n plus 1 over n plus 1, right? So super easy integral to do. And then we get this function, right? This is a power series representation of this function, of the integral of this function, right? So it takes functions that may have been hard to integrate, right? F may have been hard to integrate, but this guy right here is super easy to integrate usually, right? So it can take an integral that's hard and turn it into an integral that's easy, right? So let's consider that integral that we did above, right? So the integral above, right, we figured out what the power series was, right? We know, in this case, f of x is equal to this series, right? From n equals 0 to infinity of negative 1 to the n, x to the n plus 3 over 2 to the n plus 1, right? So we know that to be the case. That's what we had, right? So we get that the integral of f of x dx is equal to the integral of the sum infinity of negative 1 to the n, x to the n plus 3 over 2n plus 1, right? I can bring this integral inside. So this ends up being equal to this sum. N equals 0. Lots of writing, but not so bad. The only thing that I'm integrating that's in terms of x is x to the n plus 3. So I'm going to keep the negative 1 to the n over 2 to the n plus 1 outside the integral, just for ease. X to the n plus 3 dx. This is an easy integral, right? So it's just the power rule. So I'm going to rewrite the sum again. Lots of writing. Negative 1 to the n over 2n plus 1 times the integral of x to the n plus 3 dx, right? That integral is just going to be x to the n plus 4 over n plus 4, right? And then we add this c on the outside of the sum, which I probably should have left for room here because this is an indefinite integral, so we get some constant anyways, so it doesn't super matter, because if you evaluated this integral specifically, it wouldn't totally matter, right? And so that's it, right? I can simplify this a little bit, but there's no real need to simplify this here, right? So we get that the integral of f of x dx is equal to the sum from n equals 0 to infinity of negative 1 to the n over 2 to the n plus 1 x to the n plus 4 over n plus 4. Perfect. Cool. So, not so hard. The original function wasn't hard to integrate, but obviously this is easy to integrate. And if you're doing a numerical simulation, this function here is good enough, right? At least in your region that you care about, right? This will only work if we'd be integrating from, we said the interval of convergence, did we say the radius? Yeah, so you'd have to go figure out what the radius of convergence was, but that would be from negative r to r, right? This was centered at 1. You could integrate from that, and that's the only place where this is defined, right? So it just gives you an easier way to potentially calculate functions or integrals and derivatives of functions that are really hard. This one wasn't hard, but we'll show you one that I've repeatedly said throughout class is impossible for you guys to integrate. It doesn't give you a nice solution, but it gives you something that you can at least use, right? Okay, so with that, we're going to move on to our last section, which is Taylor series and Maclaurin series, right? So in 8.6, we considered the series represented by, or the series representation of functions where the function was of the form like 1 over 1 minus something, right? And that can be represented as this power series here. But that's pretty restrictive, right? There's not very many functions that can necessarily be written like that, right? For example, like e to the x, sine of x, tangent. You could dream up a bunch of different functions, log, stuff like that. Like those are all very hard to represent like this. And so we want to expand the class of functions that we can look at rather than just things that are like 1 over 1 minus x. And luckily we have a nice way of doing that, right? So we know if a function has a power series, right? We're going to assume that the function has a power series representation. And if it does have this power series representation, then we're going to figure out what its form looks like. This doesn't guarantee that it has a power series, but any function that you're given in your classes right now is going to have a power series representation. And it's specifically most likely going to have a Taylor series representation, right? So we're going to assume it does, and that means that it can be written as n equals 0 to infinity of a sub n x minus b to the n, right? This is a general power series. I haven't specified what my an and my b are, but if it can be written as a power series, it can be written like this, right? And so this is equal, I'll just write out a couple terms, a sub 0 plus a sub 1 x minus b plus a sub 2 x minus b squared plus plus a sub n x minus b to the n plus right? So, well, my goal here, the unknowns, I don't care what the b is, right? The b, I can center this at any number. The b is not really important. I could get rid of it, but I just wanted to write it in general. My unknown here is actually my a sub n. So we want to figure out what a sub n's actually give us the power series representation. Once we figure out that, we're good. So how can we get these a sub n's by themselves? Well, if we take a derivative of this whole thing, right? If I take the derivative of f, well, what does that do, right? This constant function, or, well, actually, I don't even have to take the derivative yet. Let's just evaluate this function at b, right? If I evaluate this at b, then all of these terms, this is x minus b, that becomes 0. This becomes 0. This is 0 squared, still 0. 0 to the n, still 0. All these terms go away. I'm just left with a naught, right? So I get, well, f of b is equal to a naught. Okay, well, I figured out what a naught is. Let's try to figure out a few more and see if a pattern happens. Well, if I take a derivative, my a naught goes away, and x minus b, the derivative, this a1 is just a constant. The derivative of this is 0, right? And the derivative of minus b is going to be 0. So this just becomes 1 minus 0. Yeah, this just becomes 1 minus 0, and then I just get a1, right? a1 times 1 minus 0 is just a1, right? This, the 2 comes down, and I left with my x minus b, and again, the n comes down. So it actually only gets rid of this term for the a1, and then all these terms will go to 0 when I evaluate at b again, right? So if I do f prime of b, that's actually going to be a2, right? Or a1, sorry. Right? Because everything else goes to 0, and this one turned to 0. Now, let's do f double prime of b. Well, f double prime of b becomes, well, remember, I did f double prime is this a becomes 0. Damn, let me write out a couple terms actually here. I'm going to write out this just so that we see. We get a1 plus, I said a2 times 2, a2 times 2 times x minus b plus a3 times 3 times x minus b squared, right? If I just take some derivatives of here, we'll have to imagine in the dots, we get a4 times x minus b to the 3 plus a n times x minus b to the n minus 1. Okay. Plus ... Okay. Hopefully you guys see that pattern, but just write out a couple terms, take the derivative, and see that ends up what's happening. And so when I evaluate it at b, let's see the best way to write this. I don't want to run out of space too much, but this is f prime of x. And so f prime of b is going to be equal to a1. Right, because all these terms have a b, x minus b, so when I evaluate at b, I'm just going to get 0. Right, and so you can see that when I take the derivative again, right, this term is going to go to 0. This term is going to actually be the only thing left, right, because this is going to become 1. I'm just going to get a2 times 2, right, so this is going to be equal to 2a2, and here I'm going to get this 2 is going to come down here. I'm going to a3 times 2 times x minus b to the 1 when I take the derivative here, right? And so I'm going to keep getting a pattern, right? So f double prime is 2a2, f triple prime, I'm just going to say 3 to the b, is going to actually be, well, I said 3 times 2, right? So I'm going to get 3 times 2 times a3, right? This is just equal to 3 factorial times a3, right? Let's see if this pattern holds. I'll let you guys confirm for yourself just because I'm running out of room. This is going to be equal to 4 times 3 times 2 times, is that? No, it is not going to be that. It is going to be, this is equal to, no, that's correct. Yes, that's 3 factorial. 4 times 3 times 2 times a4, which is 4 factorial a4. Okay? And this is, in fact, 2 factorial a2. And this is, in fact, 1 factorial a1. Right? And so what is f to the nth derivative value would it be? You can guess, and you would be surely right. N factorial times a sub n. Right? Okay, so if we want to determine the value of a sub n for any n, we now have this formula. We can just solve for n, right? So solving for n of this formula, we get a sub n is equal to f, the nth derivative of f, evaluated at b, divided by n factorial, right? So we know that the power series representation of any function, if it has a power series, is equal to the sum from n equals 0 to infinity of a sub n. And what is a sub n? That's f to the n times b over n factorial, right? Times x minus b to the n, right? That's just our formula. This is a sub n times x minus b to the n. That's our formula for our power series. Right? Any power series is written like that. And so what we call this specific power series is a Taylor series of expansion of f centered at x equals b, centered at the point x equals b. If we want to center it at x equals 0, right, that's called a Maclaurin series. They're the same thing. It doesn't matter, but we just have to rewrite f of x is equal from n equals 0 to infinity of f of n, right? This is centered at x equals 0, not x equals b. So wherever we see a b, we put a 0. So f evaluated at 0, n factorial, times x minus 0 is just x to the n, right? So it's just a Maclaurin series. And so we can do any of this unless the function is infinitely differentiable, which we often, we can't do any of this, right? So this doesn't work for all functions, right? It works locally for functions, but it doesn't work globally for all functions, unless that function is infinitely differentiable, right? Here, the only way I can find these a sub n's is if I take n derivatives, right? N derivatives to get an, 4 derivatives to get a4, 3 to get a3, right? So if I want to figure out what all these terms are, I actually have to be able to take the derivative infinitely many times, right? And so these are functions that are just really smooth. If they're at all pointy, or if they end up becoming pointy after you take a couple derivatives, you're not going to be able to find the Taylor series. You can find it around a certain region, but we won't get into that. If you take physics and engineering, you'll get into that. But we just say as long as the function is smooth, then we can take as many derivatives as we want, right? Okay, and smoothness, this you'll get into later, but it's exactly what you think it is. It's just a smooth, like what you think smooth is, right? but formal definition requires more work. Okay, so let's construct a Maclaurin series for this function e to the x, right? So in this case, f of x, we know f of x is going to be equal to some series of the form n equals 0 to infinity of a sub n x to the n, right? Which is a0 plus a1x plus a2x squared plus a3x cubed plus dot 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 dot. Right. Okay, so let's figure out what our things are and see if we can't figure a pattern, right? So f of 0, well, when x is equal to 0, we just get a0. That one's pretty easy, right? If we get f prime of 0, right, when I take the derivative, I get a0 plus well, actually I don't get a0, right? This is a constant, so that goes away. I just get a1 times 1, right? The derivative of x is just 1, so I just get a1. And evaluated at x equals 0, all of these other terms here go to 0, right? So I just get a1. Okay, but remember, this 2 came down here, right? When I took the first derivative. So now f double prime evaluated at 0 is going to be equal to 2a2, right? Because when I evaluate, if I take another derivative, this is 2a2x, right? 2 times a2 times x, because I took one derivative. And then when I take the second derivative, I'm just going to get a 1 instead, right? Up here, I'm going to get a 1. So this 2 is going to come down, take the derivative. This is going to become a constant, just a 1. I'm going to get 2a2, and then all these terms are still going to have an x, so they're going to go to 0, right? And then f3 evaluated 0. We'll write, if we remember, this 3 came here, and it became a 2. And then the 2 on the next derivative, right? On the first derivative, it came down, it became a 3, right? So I got, so for first step, I get 3a3x squared. Second, I got 3 times 2a3x. And then on the third, I get 3 times 2 times just a3, right? Because the x becomes a 1, right? So I get 3 times 2 times a3, which is just 3 factorial, a3. And this one's just 2 factorial. This one is just 1 factorial. 1 factorial a1, a2, and 0 factorial is just 1, and this is a 0. All right, so remember 0 factorial is 1, and if you do more of these, you'll see the pattern forms, and we get that f, the nth derivative of 0, is equal to n factorial a sub n, right? And that means, so maybe I'll write it here. So f of x is equal to this sum from n equals 0 to infinity of x to the n over n factorial, right? And this is just equal to e to the x. So what's the radius of convergence? The radius of convergence. Let's test it, right? So let's do the ratio test. Well, the limit as n goes to infinity of an plus 1 over an. This is going to be equal to the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. Put absolute value. That's the limit as this is an n, right? So I get one of these canceling with that. I just get an x in the numerator. I'm just going to put that x in the numerator by itself here. Right, the n's don't matter with the absolute value, so I just get n factorial over, I can split up this n plus 1 times n factorial. Oh, not n plus 1, n factorial, right? And I get those canceling nicely. And so this is just equal to the absolute value of x times the limit as n goes to infinity of 1 over n plus 1, which equals 0, right? So our series converges to e to the x for all values of x, right? So that's pretty nice, right? This converges exactly. This is exactly our function. It's just written in a weird way, right? And so this is how you can go about actually calculating. If I throw you in a room and say you can't leave until you tell me what the fifth hundred digit of E is, right? E is an irrational number. You can now calculate, because you can add things up pretty easy. You can say, well, f of 1 is equal to e to the 1, right? Which is just equal to e. But I know that that's just this sum, n equals 0 to infinity of x to the n, right? But x is 1, so this is 1 to the n over n factorial. And this is just equal to the sum from n equals 0 to infinity of 1 over n factorial, which is just equal to 1 plus 1 plus 1 over 2 plus 1 over 6 plus 1 over 3 times 4, what's 6 times 4, 24. And if I give you a little tiny calculator, you could calculate this, but this is how we can go about and calculate actually as many digits as we want of e. Pi is a lot harder, but it doesn't really matter. But if I locked you in a room, you wouldn't like me, but you could do it, right? So let's try a little bit of a harder example. I'll show you the harder way to do it, and then I'll show you the easier way to do it if you know your Taylor and Maclaurin series well enough off the top of your head, right? So we want, again, and I believe this is not our last example. I have two more, or this and another example. We want f of x equal to the sum from n equals 0 to infinity of a sub n x to the n, right? It's a power series, and specifically we know our Maclaurin series is going to be of the form n equals 0 to infinity of the nth derivative valued at 0 over n factorial times x to the n, right? That's our general Maclaurin series. Series, right? So we need to figure out what this pattern is. So it's going to be a little bit annoying, but f of x is equal to cosine of square root of 2 of x. So I know f, the 0th derivative of f of x, is going to be equal to cosine of square root of 2 of x, which is just going to be equal to 1 when x is equal to 0. Oh yeah, we're centering at x equals 0, right? So this is equal to 1 when x is equal to 0. In my notes that I have posted, it's when n equals 0. I don't know why I wrote that. Just change them to x's. It's when x is equal to 0. F1 of x right? If I take the first derivative of x, this is negative square root of 2 times sine of root 2 of x, right? Sine of 0 is 0, so this just ends up being 0. F double prime of x is going to be equal to negative, the derivative of negative sine is negative cosine, so I get negative 2 times cosine, because that root 2 comes out, square root of 2x. And this ends up going to be negative 2, right? When x is equal to 0, cosine is 1, and so we get negative 2. And if we keep doing this, I get f, the third derivative of x, is going to be equal to negative 2 root 2 times, oh no, not negative, positive 2 root 2 times, because the derivative of cosine is negative sine, so negative derivative of negative cosine is positive sine root 2x, which ends up going to 0, right? Because sine of 0 is 0. Okay, and f of 4 of x is going to be equal, derivative of sine is positive cosine, so I'm going to get 2. I'm going to pull out another root 2, so I'm going to get 2 times cosine of square root of 2 times x, and that's going to become a positive 4. Okay, and you might end up seeing a pattern, but if you go through, obviously the next one's going to be 0, but then the sixth derivative, x, if you go through and calculate it, it's negative 4 times 2 cosine of root 2 x, which when evaluated at x equals 0 is going to give you negative 8. So we can see that, let's see, this is, sorry, I see why I wrote the when n equals 0. So this is for n equals 0, n equals 1, n equals 2, n equals 3, right? Third derivative, n equals 4, I'm going to say 0 when n equals 5, and n equals 6. Okay, so we want a formula, so we know for our geometric series. We know we can write out the first couple of terms, right? We can just write out a couple of these and see what our formula ends up giving us. But so our first term is f of 0 over 0 factorial, that's 1, times x to the 0, that's also 1, so I'm just going to get a 1, right? So I get a 1, and maybe if I zoom out so you guys can see a little bit more, I get a 1 plus my second derivative evaluated at 0 is negative 2 over 2 factorial, right? N is equal to 2. I don't care about this 0 term when n is equal to 2, so 2 factorial x squared. So my term is 2x squared over 2 factorial, right? And if I keep doing this, I get 4x to the 4th over 4 factorial. I'm sorry, this I did a plus, but this should be a minus, right? Minus 8x to the 6th over 6 factorial, right? So let's see what's happening, right? So this ends up, it's going to be the sum from n equals 0 to infinity. Okay, so let's see what's happening in the denominator. I go 0, so I could either be 1 factorial or 0 factorial. Well, I get 0 factorial, 2 factorial, 4, 6. It seems like I'm going up by evens, right? So if it was 1, then that pattern wouldn't hold. So let's do n factorial, or 2 times n factorial. Let's do that actually. 2n factorial, right? It went up by even. Even numbers are 2 times n, right? So n equals 0, n equals, does that actually work? N equals 1, yep, n equals 2, n equals 3. Yeah, so we're good, right? Okay, and then, look, I have the 1, um, and I have a 2, and I have a 4, and then I have an 8. Well, that kind of seems like powers of 2, right? 2, 4, 8. Those are powers of 2. So let's see. 2 to the n, does that work? Well, when n is 0, I get 2 to the 0. That's just 1. So, oh, yeah, that does work, right? And then I have an alternating term, and I know that's going to be negative 1 to the n. Why do I know it's not n plus 1? Well, because we start positive, right? So our first term better be positive. Negative 1 to the 0 is 1, so it's positive. If I wanted it to be negative, it'd be to the n plus 1, because then I'd get negative 1 to the 1, which is negative 1, right? So keep that in mind. And then x to the 2n, right? We're going up by our even exponents, right? So 2, 4, 6, right? So that goes right back up there into the exponent. So now I have this power series, this Maclaurin series for square root or cosine of square root of 2 of x, right? Another way to do this is if we know, which you don't know yet, but you'll know on the next page, that cosine of x is going to be, we can derive these, and your book has them, of negative 1 to the n x to the 2n over 2n factorial. Okay, so if I want a square root of 2, I just better add a square root of 2, right? So that implies that cosine of square root of 2 times x, wherever I see an x, I'm just going to put a root 2x, right? So I get a sum from n equals 0 to infinity of negative 1 to the n. Now instead of x to the 2n, I get square root of 2x to the 2n over 2n factorial. This 2n goes to each of these, so I get n equals 0 to infinity, negative 1 to the n. Square root of 2 to the 2n is just 2 to the n, right? The 2 and the square root cancel out, so 2 to the n. X to the 2n, that one stays, over 2n factorial. It's also a lot quicker if you know the series expansion for cosine. You can just modify it, just like we did for 1 minus, or 1 over 1 minus x, right? So it's important to memorize these. They'll become useful in the future, but I mean, you don't have to if you don't want to. You can derive them. And also, one thing worth noting is we know cosine is an even function, right? So let's look down here. Cosine is an even function. Look, I have even power, or even number here. Sine is an odd function. Sine 2n plus 1 is always going to be an odd number for any integer n. So this is where that term even and odd function comes from, is from the power series, right? And so you can memorize all these. This one down here is useful to memorize, right? You'll be able to foil anything really quickly if you remember how to calculate your combination and permutation, but this is just the binomial theorem. So don't worry about that one too much, but it is good to remember. But this is k choose n. So if you want to go back and look up how to do your combinations versus permutations, go ahead and do that, but it's not too hard, right? Okay, so now we can look at this function that I always say is very hard to integrate. In fact, there's no closed form solution for it. And because of that, we can integrate it as a Taylor series. So we can use that theorem, we can write the power series representation for it, and then integrate that sum. And then if we had a computer, computers handle sums really well, we can have it calculate up to whatever degree of precision we care about. Okay. There's a much harder way to integrate this, but you'll have to wait till Calc 3 to learn that. but we'll do it here. So, well, we know. So what's the function that looks similar here is e to the x, right? E to the x is equal to this sum, n equals 0 to infinity, x to the n over n factorial, right? So that implies that e to the negative x squared, well, wherever I see an x, I'm going to put a negative x squared, right? This is equal to the sum from n equals 0 to infinity of x negative x squared to the n over n factorial, right? And I could simplify this down a little bit, maybe equals 0 to infinity, negative 1 to the n, x to the 2n over n factorial, right? A little bit easier to deal with. Okay, well, now this is going to be really easy to integrate, right? This is not a hard function to integrate, x to the 2n, right? So using our theorem, we get it's the integral of e to the negative x squared dx is going to be equal to the integral of the sum n equals 0 to infinity. I'll write it out in painful detail this time, just so that you guys all see it, over n factorial, right, dx, right, and this is equal to, I can bring the sum in, or the integral in, so n equals 0 to infinity of the integral of negative 1 to the n x to the 2n over n factorial dx. Now, you guys might get scared because this looks hard, right? This integral looks hard. But remember, what are we integrating with respect to? We're integrating with respect to x. So all of this mess right here, does this depend on x? No. So I can pull it out. I get sum from n equals 0 to infinity. I pull that junk out, negative 1 to the n over n factorial, integral x to the 2n dx. Okay, easy integral, power series, or not power series, power rule, right? This is equal integral, or sum, sorry, 0 to infinity, negative 1 to the n over n factorial. Well, the integral of x to the 2n, I add 1 to the exponent and then divide by that number, right? So this is x to the 2n plus 1 over 2n plus 1, right? Am I happy with that? Yeah. Yeah, I don't know why in my notes I have divided by n plus 1. Do I care? No. I don't see why I did that. I think that's just a typo. Just do 2n plus 1, right? And so the integral of e to the negative x squared dx is equal to just the sum. N equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over n factorial times 2n plus 1. Super easy, right? This is a super easy formula. If I wanted you to calculate like 30 terms of that, it'd be annoying, but you could easily do it. And a calculator or computer could do it way easier, okay? So, this is why these Taylor series can be so useful. Okay, so we'll do one more. So we know I'm going to just do, I say Taylor series. Taylor series are Maclaurin series, just centered at a different thing. That doesn't matter. I'll use them interchangeably. But he'll often say the Maclaurin series, or he'll say the Taylor series centered at a specific number. You can easily translate these series to that by just minusing b from x, right? That's all you have to do. And then, or at a specific number, evaluate b at that number, okay? So we're going to do this one. Well, we know that the Maclaurin series of sine of x is equal to this. If you go back up in the notes and look, it's negative 1 to the x to the 2n plus 1 over 2n plus 1 factorial. So x cubed times sine of x over 2 is going to be equal to x cubed times this sum to infinity of negative 1 to the n times, I'm just going to do a 1/2. I just don't want the 1/2 on the x. 2n plus 1 times x to the 2n plus 1. Does that make me happy? Yes, that makes me happy. 2n plus 1 over all of this over 2n plus 1 factorial. For some reason in my notes I'm just doing it x times sine of x over 2. Don't worry about that, just do x cubed. It's pretty easy to see what happens. When I put this x cubed in here, that's just going to add, when I pull this x cubed into this, it's just going to add to the exponents of this, right? So this is just going to be equal to the sum from n equals 0 to infinity of negative 1 times over 2 to the 2n plus 1 times x to the 2n. I'm adding 3 whole exponents to this, right? So it's n plus 4 over 2n plus 1 factorial. Okay, so now the integral. So the integral ends up being x cubed sine, I might run out of room, dx is equal to the integral of the sum, n equals 0 to infinity. Oh my gosh, I don't want to write this. 1 over 2 to the 2n plus 1 times, I'm sorry this is getting messy. Look at my notes for clear, but my hands are cramping at the moment, so this is as good as you get. Dx. Okay. Again, none of this matters. This doesn't depend on x. Only this depends on x. So we can just use the power rule for integration. This is equal to the sum n equals 0 to infinity of negative 1, the 1 over 2, 2n plus 1 over 2n plus 1 factorial integral x 2n plus 4 dx. All right, this is easy integral. This is x to the 2n plus 5 over 2n plus 5, right? Just by the power rule, right? So this ends up being the sum from n equals 0 to infinity, negative 1, 1/2 to the 2n plus 1 times x to the 2n plus 5 divided by 2n plus 1 factorial times 2n plus 5. Okay, and then that's it. Cool. So we took harder integrals and we changed them into easier integrals by using these power series. Now, it's not very useful to see exactly what the function is, but if you needed to numerically compute these things, so computer scientists will have to do this too if they have to compute integrals. And in fact, lots of functions are very hard to integrate. Like I said, not every function is easy to integrate. I can give you a function that's very quickly impossible for you to integrate. But if you do this power series, you can at least estimate it, right? And so if you want to look for these are in your book. in your book, I think they have more than this on page 484. Okay, so they have these and more, and more. So please make sure to go check those. Hopefully this long lecture kind of helped clear some stuff up. I don't know what I stole from your worksheet and what I didn't. So I think there's at least one problem in here that's on your worksheet. So it's a freebie. So just make sure that you look at that and try to do it. And if you have questions, let me know. Hopefully the audio on this is good because I really don't want to record this. So if the audio is terrible, just shoot me a message and let me know, but hopefully it makes sense. And again, if you have any questions, feel free to let me know. I will try to answer as speedy as I can. Other than that, you guys have a good rest of your weekend. Okay, have a good one. Bye.